Today I will discuss the theorems about finite field and Galois's field. Now see here theorem. Any finite field F with p raised to n element is the splitting field of x raised to p raised to n minus x belongs to Fp of x. Consequently, any two finite field with p raised to n element are isomorphic. In this, for proof, in the finite field F with p raised to n element, the non-zero element forms a multiplicative group of order p raised to n minus 1. Thus, if 0 is not equal to lambda belongs to p F, then lambda raised to p raised to n minus 1 is equal to 1. So, lambda raised to p minus n, lambda raised to p raised to n is equal to lambda. Also, if lambda is equal to 0, then lambda raised to p raised to n is equal to lambda. Hence, all the p raised to n elements of F satisfy the equation x raised to p raised to n minus x is equal to 0. Since x raised to p raised to n minus x belongs to Fp of x, has only p raised to n roots. Every element of F is a root of x raised to p raised to n minus x. Hence, finite field F with p raised to n elements is the splitting field of x raised to p raised to n minus x belongs to Fp of x. Let E and F be two finite fields with p raised to n elements. By previous theorem, E and F contains a field Fp and Ep, each of p elements. Also, E and F are splitting field of x raised to p raised to n minus x over Ep and Fp respectively. But since Ep is equal to Zp is equal to Fp, it follows by uniqueness of splitting field, then E is isomorphic to F. This proves the theorem. Next one theorem. For each prime p and each positive integer n greater equal to 1, the roots of x raised to p raised to n minus x belongs to Zp of x. In its splitting field over Zp are all distinct and form a field F with p raised to n element. Also, F is the splitting field of x raised to p raised to n minus x over Zp. Now see here proof. For proof, suppose that f of x is equal to x raised to p raised to n minus x belongs to Zp of x. Since f dash of x is equal to p raised to n into x raised to p raised to n minus 1 is not equal to 0. By corollary, previous corollary, f of x cannot have multiple roots. Thus, f of x has all its p raised to n distinct roots. We show that these roots form a field that is the splitting field of f of x over z. Let alpha and beta be roots where beta is different from 0. Then alpha plus minus beta raised to p raised to r is equal to alpha raised to p raised to r plus minus beta raised to p raised to r, and alpha beta inverse raised to p raised to r is equal to alpha raised to p raised to r into beta raised to p raised to r inverse is equal to alpha beta inverse. Thus, the set of roots of f of x forms a subfield of the splitting field f of x over z with p raised to n elements, and therefore coincide with the splitting field. Now next theorem, see here, next theorem. If f is a finite field with p raised to n element and m is a positive integer, then there exists an extension field E of f such that degree of E over f is equal to f, and all such extensions are isomorphic. For proof, let f bar be with the algebraic closure of f. Consider a polynomial f of x is equal to x raised to p raised to n mn minus x belongs to f of x. Since the multiplicative group of f is of order p raised to n minus 1, for 0 is not equal to u belongs to f, u raised to p raised to n minus 1 is equal to 1. Hence, so since p raised to n minus 1 into p raised to n into m minus 1 is equal to 1, then u raised to p raised to mn is equal to u. This shows that each element of f satisfies f of x. By previous theorem, the p raised to mn roots of f of x are distinct and form a field E. Therefore, Zp is equal to Fp is subset of F is subset of E is subset of F closure, and degree of F over Fp is equal to n, and degree of E over Fp is equal to mn. Hence, degree of E over F is equal to m, and this is required